Welcome to this explainer. Today, we're taking those incredibly dense Solidity docs and alchemy research papers and transforming them into real actionable blueprints for building your smart contracts. Look, whether you're laying down your very first lines of code or you're already refining complex decentralized applications, understanding the absolute structural integrity of your code is completely critical. So let's kick things off with the massive question driving literally all secure Web3 development. How do you build a secure digital fortress on the blockchain? Because think about it. Once you deploy code to Ethereum, it is out there in the wild for everyone to poke at. You absolutely have to know exactly how it operates, who can get inside, and how it guards the valuable assets it holds. And really, a smart contract is exactly like a highly secure building that manages assets through strict, unbending programmable rules. If you're coming from traditional programming, they're super similar to classes in object-oriented languages. They are your structural blueprint. They hold persistent data in what we call state variables. You can think of those as the heavy steel vaults, and they use functions as the secure doors and internal machinery that actually modify or interact with that data. Okay, here's our roadmap for today. We are going to cover 1. The Smart Contract Foundation. 2. Controlling access with visibility. 3. Function rules and mutability. 4. Optimizing storage and variables. 5. The transient storage revolution. And finally, 6. Special functions and events. Let's jump right into part 1, the Smart Contract Foundation, deploying the architecture. Picture your constructor as the initial construction crew. They show up, run exactly one time to set up your fortress's defenses, and then they're gone. Contracts can be spun up from the outside via a normal Ethereum transaction, or from the inside by another contract. But here's the catch. A contract has to know the source code of what it's creating, which makes cyclic creation dependencies completely impossible. Once that constructor does its job, its code is literally discarded. The final deployed bytecode you're left with only includes your public and external functions and whatever internal functions they need to do their jobs. Moving on to Section 2, let's talk about controlling access with visibility, effectively setting up your security checkpoints. When you're mapping out who gets security clearance, you're dealing with 3 basic types of callers: the main contract itself, a derived child contract, and a third-party outside contract. If you make a function public, the doors are wide open. Everyone gets in. Internal means only the main contract and its derived contracts have access. Private locks it down exclusively to the main contract. But then you have external, which is kind of wild. It actually denies direct internal access to the main and derived contracts, allowing only third-party callers to trigger it, unless you use a special workaround like calling this.fo. And this brings us to a massive gas optimization secret. External functions are basically a VIP fast lane. When you declare a function as public, Solidity assumes it might be called internally, so it defensively copies all the input parameters into memory, and memory allocation costs gas. External functions, though, know for a fact they're only being called from the outside, so they bypass memory entirely and read parameters directly from the call data, which makes them noticeably cheaper to run. Now, keep in mind your state variables, those internal data vaults, default to internal visibility, and logically, you can't even mark them as external. If you want the outside world to read a state variable, you just mark it as public, and the compiler automatically hands you a getter function. But please remember this. Making a variable private or internal only stops other contracts from reading it. The data itself is still perfectly visible to anyone just looking at the blockchain. Private does not mean encrypted. All right, Section 3, Function Rules and Mutability, establishing the rules of engagement. Think of view functions as your security cameras. They can observe the state of the fortress all day long, but they are physically blocked from altering anything. When you declare a function as view, you're promising it won't write to storage, it won't emit events, and it won't send ether. And this is not just a polite suggestion. For any EVM from Byzantium onward, this is strictly enforced at the protocol level using the static call opcode. If a view function tries to break the rules and modify the state, the EVM just throws an exception and shuts it down. Cure functions take this isolation a step further. They are totally cut off. They don't even look at the blockchain state variables or token balances. They just take the inputs you feed them, run some math or logic, and hand back a result. No reading storage, no reading the contract's balance, and they can't even peek at block properties like the current timestamp. So what actually counts as modifying the state? Well, the EVM is super strict about this, so you know exactly when you're altering the fortress. It's obviously writing a new value to a variable or transient storage. But if you emit an event for some off-chain app to listen to, that's a state modification. Sending ether, creating a new contract, or calling another function that isn't view or pure,
all state modifications. Knowing these rules inside and out is how you use View and Pure to make your code as safe and cheap as possible. On to Section 4, optimizing storage and variables. Let's secure those vaults. There's a really crucial difference between constants built directly into your blueprints and immutables that get finalized during that initial construction phase. Both are absolute game changers for saving gas because neither one uses a traditional expensive storage slot. With a constant, you have to know the exact value the moment you compile the code. But immutable variables give you a bit more breathing room. You can actually calculate and assign their value dynamically inside the constructor, like, say, saving the address of the person deploying it. And once deployment is done, that value gets permanently baked right into the deployed bytecode. Now, the magic number to remember here is 32. 32 bytes are always reserved for immutable values. This actually explains why a true constant can sometimes save you just a tiny bit more gas. Even if your immutable variable is just a simple Boolean or a tiny integer, the compiler sets aside a full 32-byte chunk of space for it in the code. Constants, on the other hand, are just swapped in wherever they're called, so they can sometimes sneak by a little cheaper. Okay, Section 5. This is a big one. The transient storage revolution, or issuing temporary visitor passes. So what if you just need to hold on to some data for a single transaction? In the past, you were stuck writing to a permanent storage slot, and even if you were a good citizen and set it back to 0 at the end of your function to get a gas refund, the upfront cost was still just painfully high. Enter EIP 1153 and the Cancun upgrade. This gave us the T-store and T-load opcodes. Transient storage securely holds data just long enough for the transaction to execute, and then, poof, it completely vaporizes back to 0. It acts exactly like normal storage, but it lives in a totally independent address space. And this is a total game changer because it completely avoids permanently bloating the blockchain. It offers a radically cheaper way to handle things like reentrancy locks. A reentrancy lock basically just stops a contract from being called again while it's in the middle of executing. Using expensive permanent storage for something that only matters for a fraction of a second made no sense. Transient storage drops that cost dramatically. But hey, quick reality check. There is a catch here. If you don't clean up your transient visitor passes, you risk breaking complex multi-transaction applications entirely. The EVM guarantees composability, meaning multiple calls to your contract can happen within one bigger transaction. If you set a transient reentrancy lock and you don't spend the tiny bit of gas to manually flip it back to false before your function ends, any subsequent call to your contract within that same transaction is going to fail. Bottom line, always clear your transient storage completely at the end of a call. Finally, Section 6, Special Functions and Events. These are your fortress alarms and safety nets. Your receive and fallback functions are your literal safety nets for incoming Ether. If someone just sends plain old Ether to your contract without specifying a function, the receive function catches it. But watch out, it only gets a tiny 2,300 gas stipend to work with. That's barely enough to emit an event, and absolutely not enough to write storage. If someone calls a function that straight up doesn't exist, your fallback function catches that error. And speaking of errors, custom errors are this fantastic, super gas-efficient way to tell the user exactly why a transaction failed, which completely replaces those older, super expensive text string error messages. Meanwhile, events write to the blockchain's transaction logs, which is how you trigger off-chain apps to listen for specific activities going on inside your fortress. So, to wrap up this explainer, I want to leave you with this thought. Every single line of Solidity you write is a structural decision. From optimizing your function visibility to save on cal data gas, to leveraging that sweet new transient storage for cheaper reentrancy locks, your choices literally define the security and the efficiency of your digital fortress. So how will you architect your next smart contract to be both impenetrable and gas efficient? Thanks for diving into the blueprints with us today.